You guys care to see our pictures from the break? Do you care? The right answer is yes, you do care. All right. Let's see. No. Let's see. This is, I think I showed y'all, we went to the zoo. I tell y'all about that? We went to the zoo over the break. We got to hang out with the monkeys. And while we were there, something very cool that's never happened to me before happened. Where is it? There it is. So while we were there, a monkey got out of the cage, and they took all the people in the zoo and crammed them into that little restaurant in the middle of the zoo. Was anybody there? It was Good Friday, so it was packed. Yeah, we were there. And so they put us all in the restaurant, and this is us just sort of waiting to get back out. It was just like one of those little, I forget what they're called. They're black and white, sort of long fur, and it just jumped out of the enclosure. And then they crammed everybody in this restaurant for like half an hour. And there were people all walking around with their big nets and stuff. It was like Curious George or something. So we went to the zoo. See, we had Easter. Went to our church for Easter. The kids have like a little Easter egg hunt thing, so that's what they were doing. That's my boy right there. He used to wear his shirt all buttoned up all the way up to the top, but now he's gotten into like having it unbuttoned. He likes to have like the top 3 buttons unbuttoned. He looks like a slick guy. Let's see. Me and my wife. And then over the break, my wife and I went to University of Florida. We went there for a conference. It was Stars to Life. We studied star formation, both she and I, and this conference was about star formation, sort of how stars form, but then also how does that lead into the possibility of other life forms on other planets, exoplanets, they say. That means planets around other stars. But while we were there, we also sort of saw some of the sites. They had a museum at UF, the Natural History Museum. That's my wife. The Titanoboa. Have you ever heard of this? The Titanoboa is this snake that was discovered down in Colombia. There was a coal mine, and when they went to excavate the coal, they found a whole ecosystem of fossils, and they found this vertebrae that was about, I don't know, the size of a little saucer, about this big, a vertebrae, and they identified it as a snake vertebra. Have you ever seen a snake skeleton? Like a large snake, a vertebra, might be 6, 8 feet. A vertebra is about this big, and this vertebra was like this big. And so they estimated this snake was about 40 feet long and about a ton, more than a ton. Yeah, so they found a lot of the bones and were able to reconstruct most of the skeleton. But this was a model of it. It's eating a crocodile, like a giant crocodile there. So that was pretty cool. That's Titanoboa. You can look it up online. There's all sorts of cool stuff about it. And then we also went to Paynes Prairie. Have any of y'all ever been to Gainesville? You have been to Gainesville? Yeah, so Paynes Prairie is, let's see, I guess I just have this picture of us. But if you look in the background, there's this big prairie, and there's bison and wild horses that live there. But the cool thing about this is that, you know, in Florida there's a lot of limestone, and when limestone gets wet, when water goes into it, it erodes it away. And so you get a lot of sinkholes, kind of like the sinkhole that was in Louisiana recently they've been talking about. And I think there was one in Florida, the guy's house sunk into it or something, right? Yeah, anyway, so they get a lot of these sinkholes, and in Paynes Prairie, all the water that falls onto that area for many miles around, 20, 30 miles, all that water drains down into this huge sinkhole that's sort of in the middle. It's like a big bathtub, and all the water just drains into it. But about in the early 1900s, that sinkhole got clogged up somehow. They don't know how, but it got clogged up. And so when the water went to drain, there was nowhere to go. So it created this huge lake. It was about 20 miles across. And this lake filled up in a matter of weeks with the rain coming in on it and various streams and stuff flowing into it. And the whole city just sort of built up around this lake. People were fishing. There were fish camps all around it, people building businesses around the border of the lake. And then about 20 years later, that sinkhole came unclogged somehow. And in a matter of about a week, that whole lake was just gone. And they said they had a big fish fry like for the first day, but then the fish, they all started rotting, and it just sort of became this noxious scene. You couldn't even really go down there for a long time. So that was really cool. I think Payne's Prairie. It's in between Gainesville and Orlando. So the wild horses. We saw an eagle's nest. It's kind of cool. All right. I think last time we left off with beats. Oh, and by the way, I just put the homework up today for this chapter. Well, there we go. We talked about beats and how when you have two waves that come together of different frequencies, I drew this figure. This figure's in your book too. I drew this on the board last time. If I have a wave that looks like that, remember we described several things about this wave. The wavelength is the distance from peak to peak. The frequency is the inverse of the period, and the period is the time between successive peaks. So remember, frequency and period are related in that way, and then velocity of the wave and the wavelength and frequency are also related. There are several homework problems, and we worked through some examples in class just on how those are interrelated. And you should expect some problems on the next quiz regarding velocity, frequency, and wavelength. So anyway, so if we have a wave that's like that, and then we have a wave that is slightly different frequency, let's see if I can do this. A slightly different frequency, then at particular points, like say for example here and here, what kind of interference will I get there? What is that type of interference called? Remember, there are two types of interference. There's constructive interference and destructive interference. And what is that one? Is it last time? What is it? Oh, no, that's constructive. You're right. I'm sorry. It is constructive. Anytime that you have a trough and a trough that add up, or a peak and a peak that add up, then you're going to get a bigger wave. Okay? So there, that would be constructive interference. What about right in the middle? Right there, what is that? Constructive or destructive? That's destructive. So I have a peak lining up with a trough, and it's going to cause that wave to basically just go away. I played some tones. We're going to sort of pick up there. So remember, this was the 300 frequency tone, 300 hertz tone. That's the 300 hertz tone. And then if you mix it with a 305 hertz tone, you hear that destructive and constructive interference coming in because it goes wah, 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 wah. And where you have no sound, that's where you have destructive interference. And where you have a louder sound, that's where you have constructive interference. So that's a nice little demonstration of this interference. So we also see it in mechanical waves, and we also see it in light waves as well, which we'll see maybe before the end of the semester. I'm not sure if we said this, but with these beats, you can determine the frequency of the beats. The frequency of the beats is equal to the difference in the two frequencies. So when we had the 300 and the 305 hertz tones, what is the frequency of the wah, 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 wah? How many times per second? If I had a 300 hertz tone and a 305 hertz tone, and then I mix them together, right, there are 5 beats per second, or 5 hertz. So the frequency is just the difference in the two tones, F2 minus F1, we'll call it. I'm going to call this delta F, or F2 minus F1. Now, where is it? There it is. Okay. I can also mix up a whole bunch of different tones. And actually, when we're listening to things, we hear many different frequencies, especially if we're in a very crowded place or if we're listening to music. We have all sorts of high and low and intermediate frequencies that are coming together to create the sound that we're listening to. Even the human voice has a lot of different frequencies within it. And so you can get very complicated tones with these beats. And it works very much the same way as this figure where I'm adding up two waves, except we just have a lot of waves. And so, for example, if I were to take a lot of different waves and add them all together, there's a figure in your book like this, but it might look something like this. Just where you get this superposition of a lot of different waves added together. And it's just going to sound sort of like a big jumble of sounds. Here I've taken 300 hertz to 310 hertz, but I've added up 5 different tones. So like I did 300, 302, 304, 306, 308. I guess I did 6 tones, 310. So I added all these different tones together, so you get this combination of all sorts of different hertz, all sorts of different beats. So obviously when you have multiple frequencies, when you're adding them together that way, the whole beat equation where we're trying to determine the number of beats isn't as simple as that because you have to disentangle them some way. And so we won't do that. But the human ear does disentangle these different beats and these different frequencies very easily. Or not easily, but it does it pretty well. All right, so this is multiple frequencies. Multiple frequencies, just adding up multiple frequencies. And the human ear, and more importantly, the brain, because the human ear is just a device, but the brain interprets those signals. To untangle these multiple frequencies. We can do this mathematically, but the brain does it because it does it. Untangle multiple frequencies. Like, for example, if you're at a party and you have multiple conversations going on, listening to multiple sounds as we often do. I have a little clip which is just about how the ear works and how it untangles these multiple frequencies. It's really quite fascinating, sort of how the ear works. There we go. It's just a couple minutes long. All right. A couple more things about resonance. You just need to know that resonance is this force vibration and that every object has a particular natural frequency. Also, there is a fundamental frequency, and then there are what we call overtones. Fundamental frequency is the lowest frequency at which an object resonates. But an object can actually resonate at multiple frequencies, and those multiple frequencies are called overtones. And those are just other natural frequencies that resonate. All right. So like, for example, the little wooden box that's going around, that's the fundamental frequency at which it resonates. But there are also other frequencies, which you may or may not be able to hear, which also resonate. Right? So we're going to look at the Doppler effect, and there are some homework problems regarding the Doppler effect. And you might even see some type of calculation on the next quiz, the Doppler effect. You've probably all seen this, right? If a car is driving along the road towards you and they honk their horn, what happens to the frequency of the horn? Is it increased or decreased from its actual frequency? or a train that's coming along the train tracks and it honks its horn is what happens to the frequency of the horn as it approaches you and then as it moves away. Right, it increases as it comes towards you, and then it decreases as it moves away. It's like, and then it decreases as it moves away. And that's called the Doppler shift, or the Doppler effect. We see a similar thing with light as well, though the physics, of course, is a little bit different. The Doppler effect. So when a source of sound is moving towards you, the frequency is shifted higher. All right, and then vice versa, when it's moving away from you, or in contrast, if it's moving away from you, then the frequency is shifted lower. Yeah, I think I have a couple of videos with trains. Let me look and see. I'm not sure if I brought them. No, I'm sorry. I guess I didn't bring them. Oh, here we go. These are just audio files of horns or trains. So you hear this is a diesel truck, as it's moving towards you, the frequency, this is a person standing here and the truck is coming along, and then you see an increase in frequency, or you hear an increase in frequency, it goes higher, and then as it moves away, it goes lower. I have another one. So that's increase in the Doppler shift. You can sometimes hear this with these tuning forks. I'll pass it again around, see if this works. Take the tuning fork, I'll pass it around, and you can move it, David. You can move it back and forth, and you'll hear an increase in frequency as you move it towards you, and a decrease in frequency as you move it away from you. I'm going to pass this around as well. Yeah, David? Right, the source is coming towards you. Right, yeah, the actual source is coming towards you. And so what it's doing is, you know, the waves travel at a particular speed, but then as this source also is traveling towards you, it's giving an additional speed, and that causes the frequency of the sound to increase. You can try that with the tuning forks as well, and I've passed around another one. Just move it back and forth, and you can hear the Doppler effect as you move it back and forth. All right, we can calculate this shift in frequency. So my observed frequency, and this will be on your equation sheet, but you should know how to apply it. And there's a homework problem just asking you to apply it. The observed frequency is the velocity of the wave divided by the velocity of the wave plus the velocity of the source. Actually, it's plus or minus. If it's moving away from you, let's see how this works. If it's moving towards you, make sure I get it right here. See, so your frequency is going to go up. If it's moving towards you, it's negative. If it's moving away from you, it's positive. So the negative is if it's moving towards you, and the positive is if it's moving away from you. You should know if it's moving towards you, you're going to get an increase in frequency. If it's moving away from you, you get a decrease in frequency. And so you need to make sure that the frequencies are matching up with that sort of model times the frequency of the source. All right, let's just do sort of a quick little example. say one of these tuning forks is the frequency of our source is about 300 hertz, and it moves, the velocity of sound is right around 300 meters per second. It's actually about 340 or so meters per second. Of course, that changes depending upon the temperature and the pressure of the atmosphere in which it's traveling. But we'll just say 300 meters per second is the velocity of the wave. And then let's just say that the velocity of our source, that is how fast you're moving it back and forth. I don't know, let's say 10 meters per second. That's pretty fast, but let's just say 10 meters per second. And then I can calculate then what is my observed frequency. Let's say that we're moving it towards you, towards the observer. And if I'm moving it towards the observer, I should see an increase or decrease in the frequency. An increase or decrease? An increase in the frequency. It should be a higher pitch sound. As you're moving it towards you, you should hear a higher pitch. All right, so I have this moving it towards the observer, and so I can calculate my observed frequency. My observed frequency is the velocity of the wave. That's the velocity of sound, 300 over 300 minus 10 meters per second. That 10 meters per second is the velocity of the source times the frequency of the source, which is 300 hertz. See, that'll give me 300 over 290 times 300, which gives me 310 hertz. 310 hertz. So when I'm moving towards the observer, I get this increase in frequency. And if I'm moving away, from the observer, my observed frequency is very similar. It's 300 over 300 plus 10 times 300 hertz. And so that's 300 over 310. I get 290 hertz. You're probably not moving it at 10 meters per second, but when you move it back and forth, you're probably hearing on the range of a few hertz difference in the frequency, moving that tuning fork back and forth. Let's see, can I collect some of my business? Thank you. Is there one more tuning fork out there? Still rotating around? You got it? Did y'all get to try the Doppler Effect? You did? Okay. Okay. We tried to start with it. There's a homework problem where you have to calculate this Doppler shift. It could very well see it on the next quiz. So just make sure that you're able to do that. You'll have the equation. Just make sure that you're able to use it properly. Any questions about that? Doppler shift, as you have a source of sound that's moving towards you, you see an increase in frequency. As it's moving away, you see a decrease in frequency. You could see just sort of some conceptual questions like that. Like if a truck is moving towards you and honking its horn, does it appear higher or lower pitched? It's pure higher pitched. And then also be able to calculate what is the observed frequency given a certain velocity of the wave. As I said, there's a homework question. No good? All right. There's one more thing in this chapter. It is sonic booms. Let me check something. A sonic boom occurs when a source when a source of sound travels faster than a wave. You've probably seen these before, or heard them before when a jet flies over and you hear a loud boom. That's the sonic boom, but they're actually more common than that. You may or may not have heard a sonic boom, but they're actually quite a bit more common, and you've probably seen them before because you get a similar effect that occurs in water when you have a boat that travels through water at a modest speed. Anytime you have a wake, that's a type of a sonic, or that's a type of a boom. So if I have a boat, this is my boat, and it's traveling in this direction, and it generates these waves, right? And you actually get this bow shock that comes out in front of it. And basically what you're getting here is because the boat is traveling at a speed that's faster than the waves, then the waves are basically catching up with one another. And when they do catch up with one another along this bow shock, you get a particular type of interference. What's that interference called? Is it constructive or destructive? It's constructive interference. All right, so those peaks and peaks are adding up, and that's what causes the boom when you have a when you're in water and there's no boom, but you can see the bigger waves adding up together, or if you have a plane going overhead, a jet, and it creates a similar thing, but you hear it because you have these sound waves that are adding up with constructive interference. So here along the shock wave, you get constructive interference. You don't have to be going that fast. I mean, a duck can create a boom too. I think actually on the homework, I think I show a picture of a duck that does it. And so this also occurs if you have a jet that's flying, and if it exceeds the speed of sound, it'll create this shock wave, which occurs because of this constructive interference. All right, let's see. I think that's the end of Chapter 8. We're going to move on into Chapter 10 right now. Is my tuning fork still out and about? Are y'all still looking at it? Oh, are y'all done? Did y'all get to see it, Royal? Any questions about Chapter 8? Yeah, Ruth. Is that when it's scheduled?
Yeah. So we're just starting Chapter 10 today.
Yeah. I'm going to send y'all an email. We might not have it next Tuesday. That's quiz 4, right?
Sure.
I think it's quiz 4. Have we had 3 quizzes already? Yeah. I'm thinking about something. I'll send y'all an email later today or tomorrow and get your input on it, okay? All right. But probably not next Tuesday. I'm sorry. I don't like to change the syllabus, but I'm thinking about making a change on it. Huh? That'd be fine. Okay. All right. Yeah, I'll send y'all an email later today. And I'll do a little online survey to sort of see how you feel about changing it. All right, we're going to move on into Chapter 10. And Chapter 10 is on electricity and magnetism. A lot of the stuff that we'll do is pretty basic, but we'll also get a little bit into circuits, sort of simple DC circuits, and how we use electricity in circuits. And then probably the very last chapter that we'll probably do one more chapter, will be on light and optics, sort of some basic geometric optics, how light travels through mirrors and lenses and what have you. The Chapter 10 is on electricity and magnetism. I'll try to get the homework up soon. We're going to talk both about static electricity and then the flow of electricity. But this first part shows you some things about static electricity. Static electricity is when electrons are stationary. Early in the 20th century, they created this model of the atom. You know about this, I'm sure. But it wasn't actually that long ago that it was discovered or proposed that an atom is made up of protons, neutrons, and electrons. And anytime we're talking about the flow of electricity, we're going to be talking about the flow, typically, of electrons. Why would we talk about the flow of electrons and not other charges? Any idea? When you think about the atom model, the model of the atom, why would we talk about the flow of electrons and not protons typically? Right, they're outside. Well, protons can move around too, but because they're outside, they're really easy to strip away. So those electrons are easy to strip away, whereas protons aren't as easy to strip away. So typically when we talk about electricity, we're going to be talking about the flow of electrons, so we'll see sort of a counterexample to that later when we get into circuits. When we're talking about charge, it has a number of properties that we'll need to consider. Charge, there are two types of charge. There's positive and negative. The positive charges are protons. The negative charges are electrons. And protons and electrons both have the same but opposite charges. So P and E, protons and electrons, have same but opposite charges. That particular charge, which we call E, is the fundamental unit of charge. Let's see, I'm not sure if it does come up. Yeah, so the fundamental unit of charge. And it has a value, which you don't need to know, but it will be on the equation sheet. It might come up in some of the problems. It's 1.6 times 10 to the minus 19. And the unit for charge, the basic SI unit, is the coulomb. C-O-U-L-O-M-B. This is abbreviated with a capital C. It was a person, so we capitalized the abbreviation. So there are two types of charges, positive and negative charges. Most things, however, are not charged at all. Like most of the time, we are not charged, and most common objects are not charged at all. Most objects are neutral. What actually, you're at any given point, you are charged, right? At least you might get an excess. Well, first of all, what does it mean to be neutrally charged? What does that say about the protons and electrons in or on your body, right? You have an equal number of protons and an equal number of electrons. But you can become charged, right? That is, the surface of your skin can become charged. And that means that you have an excess of one or the other. Now, typically, almost always, that's going to mean that you have an excess of electrons. When I went to this school, this math and science school was a boarding school, and so we shared dorms. And I remember one night, I shared a room with a good friend of mine, Chris Reeks. He was the guitarist in our heavy metal band. And Chris, he always went to bed early, but I stayed up late. But I remember being up late one night, and he was over there asleep, like we had bunks or whatever, and he was asleep. And I said, well, I'm kind of bored. And so I stood up and I started shuffling my feet on the carpet. And then what would I do? I went and I touched his ear. I didn't touch his ear. I just got my finger really close to his ear. And it was pretty cool. It was very dry day. And you could actually see the discharge of the spark from my finger to his ear because the lights were out. We were not supposed to be up. And he would just sort of twitch. He didn't wake up. But in that case, I do become charged because when you rub your feet on the carpet, you're actually taking electrons from the carpet and depositing them onto your body. And then you have this excess of charge on your person. Now, within your body, you can also have regions that are charged in one way or another, which I think is more what you were asking. Okay, yeah. Okay, well, I don't think that any one person has a bigger propensity to be charged, but there are particular days when you can be charged more than others. Uh, when do you experience shocks more?
On Friday.
On what? On dry days, cold days, because they're dry, because cold days, the humidity uh, condenses out of the atmosphere. But on dry days, and the reason that is that if it's a very humid day, as it often is around here, the humidity actually takes the charge away. Water is a polar molecule, and it sort of has this, what's the word? It's sort of this, it's not charged, but the positives and the negatives are separated, and so they can take away charges more easily. Chemists have a name for it. I forget what it is. What? Yeah, I guess so. You can wear one of those hats that spray out the water, like they have in the summertime with the little fans on them, and sort of create this cloud around you all the time, and then you won't be charged anymore. All right, so most objects are neutrally charged, but you can get an excess of negative charge. All right, the second property, we'll call this the first. There are two types, positive and negative. This, sorry, y'all get all that? Okay. All right, the second property is that charge is conserved. That means it can neither be created nor destroyed. The third property is that charge is quantized. This means that if you have a negative charge, it's always going to be some integer value of the charge of an electron. Or if you have a positive charge, it's always some integer value of the charge of a proton. That means that you can't have a half of an electron, or you can't have a half of a proton. That whenever you have charges, it's going to be 1.6 times 10 to the minus 19 coulombs, or it's going to be 3.2 times 10 to the minus 19 coulombs, or 4.8, or excuse me, yeah, 4.8 or 6.4, some integer value of the number of electrons. You're going to have 1 electron, 2 electrons, 3 electrons, but you're not going to have 4.5 electrons, or you're not going to have 2 1/3 electrons. And so that means that it's quantized. It comes in particular quantities. It's quantized. So you can have 1 electron, you can have 2 electrons, you can have 3 electrons, but not 4.5 electrons, right? Because charge is quantized and it comes in particular quantities. All right, the fourth thing and the final thing that we'll consider is that like charges repel. And opposite charges attract. Cool. All right, going to get into a couple of mathematical things. We're going to sort of just do Coulomb's law. This is very similar to Newton's law. Remember Newton's universal law of gravitation, which described the force between two objects of mass, where we had that constant G times m over r squared. And there is a gravitational force between every body that has mass. Just like there's a gravitational force between me and the Earth and me, there are gravitational forces between all of us. They're small, but not unmeasurable. In a similar way, we have Coulomb's law, which describes the forces between charged particles. And it looks very similar. Coulomb's law describes the force between charged particles. And it says that this force is equal to K Q1 Q2 over R squared. So here I have two charges. This will be Q1. Q1 is just a measure of the number of coulombs of the charge. So if this was an electron, for example, it would be 1.6 times 10 to the minus 19. This would be Q2. And then the distance between them is R, and K is called Coulomb's constant. And it's equal to 9 times 10 to the ninth. Let's see, that's Newton meter squared per Coulomb squared. I'll do a quick example, but it's going to be fairly basic examples. If I have a couple of charges, what is the force acting between those two charges? And there will be some in your homework for you to work through as well. I go down from here. I'll give y'all just a second. Let's see, have I told y'all my desert joke? I'm not sure. Have y'all heard the desert joke? No? All right. Why does nobody ever go hungry in the desert? You say, I don't know. No, they don't have dessert. Because of all the sandwiches there. You get it? Sandwiches there. Sandwiches. All right. Can I go on now? All right. Let's do a quick example. Let's say I have two electrons. Actually, let's do an electron and a proton. I have an electron and a proton separated by 1 micron. What is the force equal to? What is the force? An electron and a proton are separated by 1 micrometer, or 1 times 10 to the minus 6 meters. What is the force acting on those? So here's my electron here. Here's my proton there. And they're separated by 1 times 10 to the minus 6 meters. And I just want to know, what is the force? First of all, what is the direction of the force? That is, are those two particles, are they going to be attracted to one another? Are the forces going to be towards one another? Are they going to be opposed to one another? Attractive or opposing? They're attractive because opposite charges attract, positive and negative charges attract, and then like charges repel. All right, so I'm going to have, did I write that actually as one of the properties of charge? I did? Okay, yeah, so my forces are going to be in this direction. I have two forces, one acting on each, and they're both going to be given by Coulomb's law. And that Coulomb's law is F equals K, Q1, Q2, over R squared. That's 9 times 10 to the ninth. Newtons meter squared over Coulomb squared, times my charges. And for the electron, it's 1.6 times 10 to the minus 19 coulombs. For the proton, it's the same, divided by my distance, 1 times 10 to the minus 6, and then that's going to be squared. And so I can work that out, find the that's Coulomb's constant. That's K. I'll give it to you. It'll be on your equation sheet. It's similar to when we had the gravitational force, the Newton's universal law of gravitation. There was a gravitational constant. Let's see, I get 2.3 times 10 to the minus 16. Is that wrong? Okay, the Q's come from the charge of a proton and an electron, and a proton and an electron have the fundamental unit of charge. That was on the previous page. The E is 1.6 times 10 to the minus 19. It's under the charge. You need to know that that is the charge of a proton and an electron, right? Okay, so protons and electrons do have opposite charges. Whenever you're using Coulomb's law, just disregard the signs of the charges. So you just write the magnitudes of the charges. Got it? That's the fundamental unit of charge. That is the charge of a proton and an electron. It was on the previous page. Yeah, I gave it to you on the previous. Huh? Not always. Like on the homework, you might have different charges that aren't protons and electrons. But you do need to know that the charge of a proton and the charge of an electron is the same and that they're both equal to this value. You don't need to know this number right off. I'll provide it to you on the equation sheet. But you need to know that they have this fundamental unit of charge. R is the distance between the two objects. Yeah, I was given here as 1 micron. 1 times 10 to the minus 6. Coulomb's law. Yeah. If it's confusing you, don't worry. Well, there'll be some more examples for us to work through. David? Okay, K is Coulomb's constant. That's just a constant. It's 9 times 10 to the 9. Okay. Q are the charges. Proton, they both have the same but opposite charges. And that's equal to that fundamental unit of charge. And then R is the distance between the charges. You can do that. It doesn't matter. All right. I got 2.3 times 10 to the minus 16. Anybody else try it? 2.3 times 10 to the minus 16? Okay. Let me try it again. Can I borrow your TI? So I'll come back. I'll give you all the chance to do it later. Anyway, it's a small number. I'll come back next time and tell you what the number is, but you can try it on your own too. All right? All right. So that's Coulomb's law. And as I said, you'll have some examples in the homework to work through, but they're nothing more complicated than this, where I'm giving you the charges of the two particles and the distance between the particles, and then you just have to find the force acting on the particles. This is pretty fundamental to the atomic model of the atom, because the electronic forces are important, the forces between charged particles in the model of an atom. David? That's right. You always have to convert it to SI units. Now, on the test, I would probably give it to you in meters, almost certainly. I think it's going to micron. Does that answer your question? All right. We're going to look at electric fields a little bit. These can get fairly complicated. I just want to sort of brush over them because you might hear about them elsewhere. especially in the years to come. And then I have a short video, and then we'll wrap up. Electric fields. This is sort of a theoretical construct that we use to describe the force that acts on a charged particle. It's a field that surrounds a charged particle and carries the force. Let's sort of put that in parentheses. To all the charges around it. And this is a lot like the gravitational field. The electric field, you don't need to know this right off, but I just want to write it. The electric field is equal to the force over the charge. So if I have a charge over here, Q, I can draw electric field lines emanating outward from it. These are called field lines. And they just describe the force, the electric force that another particle will feel if they come up in the vicinity of this charge. Just finish drawing them. Symmetrical. So if I were to take another charge, say a plus Q right here, and I move it over here, then it's going to feel a force that's in the same direction as the electric field lines. So the electric field is really just this way that we describe the force that charged particles feel. All right. Just sort of need to know that. The electric field is a way to describe the force that a charged particle feels. And we can get very complicated in sort of how we use these. I just want you to know that it surrounds the charged particles, and it sort of carries the force to all the charged particles. And then also, another way of thinking about it is it describes the force that a charged particle feels. These become very important when we're talking about electric circuits and what have you, though we're not going to deal with them in terms of electrical circuits because we'll deal with sort of in a simpler basis. But the reason I want you to just sort of know what it is and know the definition of it is that it's becoming more common to use these in medical applications. We use electric fields for a lot of things, like the old TVs, the CRTs. You ever had any of those TVs? The big ones with the big wide TV? Those used electric fields to direct charged particles onto the back of the screen. Today, with flat screen TVs, they're different. But with the older TVs, the big CRTs, the cathode ray tubes, they used electric fields to change the direction of charged particles. Anytime you have an inkjet printer, those use electric fields to direct charged particles onto your paper, charged particles that carry ink. 3D printers, these new 3D printers that are coming out, work in a similar way where they use electric fields to direct the position of charged particles. And so it just describes the force that these charged particles feel. I have a little clip here. This is from a TED Talk. TED Talks are these, I think it's Ted Turner. He brings in these people that are sort of cutting edge, doing cutting edge research. And there's this one guy who's talking about electric fields and how these electric fields are being used now to, or at least experimentally, to treat cancer and might actually show a promise in sort of a non-invasive way of treating cancer without damaging the rest of the body. So let's watch this. It's kind of exciting. I know everybody knows somebody that's been impacted in some way by cancer. So here we go. We'll wrap up with this.